Hey everyone, this is Mr. Wistar again, and in this unit we're going to take a look at a couple of important searching algorithms that you need to know in this unit on sorting and searching. So what are we talking about when we talk about searching? Well, unlike sorting, searching involves taking a collection of data and looking for a particular value. Depending on what the purpose is of our searching, we usually are going to write a method that returns either true or false based on whether it succeeded or not, or an integer corresponding to the position where we find the first match for the target that we're looking for, depending on what our application is. In this lesson, we're going to take a look at two algorithms. One is called linear search, and the other is called binary search. Linear search is probably the simplest way that you could ever think of if you were trying to find something in a list of data, and it's literally as simple as starting at the first element, looking at the first element, then the second element, then the third element, then the fourth element, until one of two things happens. Either somewhere along the way you find the thing that you're looking for, or you reach the end of the list. And that's exactly what you see in the pseudocode here. If the if statement is true, then we've found the thing that we're looking for and we should return true. Otherwise, if the loop reaches the end and actually quits, then that tells us that we didn't find what we were looking for, so we should return false. That's how linear search works. It's pretty much the simplest searching algorithm you could possibly come up with. But, as you might guess, it's not exactly the most efficient algorithm. And so we're going to also study a second searching algorithm in this lesson called binary search. Binary search is a lot faster for reasons that we'll talk about in a minute, but it has a limitation, which is that it only works with arrays that are sorted. And the reason why is because of the way that it works. It's kind of like that guessing game that you probably played when you were a little kid, where you ask somebody to pick a number, and then you just keep making guesses, and the person will say, no, no, too high, or nope, too low. And well, if you were a little kid, you probably weren't smart enough. You probably just kept asking numbers that were bigger or smaller depending on what the person said. Binary search is a little more precise than that. The idea is that if we think about our array in the beginning as being an entire collection of numbers that might or might not contain the thing that we're looking for somewhere in there, what we do is we take the array and we go to the exact middle. Remember, it's sorted again, so that exact middle is greater than everything that comes before it and less than everything that comes after it. And so if we take the item that we're looking for and compare it to the middle, if the item we're looking for is less than the middle, then that tells us that we can just focus our attention on all the stuff that comes to the left of the middle, or the stuff that comes before the middle. On the other hand, if the thing that we're looking for is bigger than the middle, then that tells us that we have to look in the right half. And then we just repeat that process all over again. So we'll take the left half, go to the middle, check and see if the target is greater or smaller than the new middle. And based on that, we're going to either look in the left half of the left half or the right half of the left half, and so on and so on and so forth. And again, one of two things is going to happen. Same thing with linear search, but a little bit more complicated. We're either going to stumble upon the thing that we're looking for, in which case our algorithm can return a success value, or what we're going to do is we're going to get down to the point where the size of the subsection of our array that we're still looking at, the subsection that might possibly contain what we're looking for, if the size of that reaches 0, then that tells us that the thing that we're looking for isn't in the array anymore. And in that case, we can return whatever our fail condition is. So let's see what that looks like in pseudocode. Bear with me. This code might look a little confusing, but if you go through it step by step, it should make sense. We got a binary search algorithm. Just like linear search, it has the same set of parameters. It's got the array that we're looking into, the number of elements it contains, and the thing that we're looking for. This algorithm depends on two local variables. Well, three, but we start off with two, and they're called low and high. And you should think about them as representing the boundaries of the slice of our array that might still contain the thing that we're looking for. So at the beginning, that slice of our array is the whole array. So we're going to set low equal to 0 and high equal to n minus 1. It's important to notice that these two indexes are inclusive. We're going to be searching everything with index greater than or equal to low, and we're going to be searching through everything with index less than or equal to high. So once we've set up those two variables, we're going to have a loop. And the loop is going to run as long as low is less than or equal to high. In other words, as long as the size of the slice is greater than or equal to 1. If we ever get to the point where low is greater than high, then the size of our slice has become 0 and we fail. But assuming that's not the case, then what we're going to do is we're going to go to the middle. Remember, that's how binary search works. That's how we make good guesses. And so the middle is just the average of the two low and high indexes. And we're going to take a look at that and see if it matches what we're looking for. That's our success condition, remember. So in that case, we're going to return whatever the success value is for the way that we're implementing binary search. If that's not true, then there's one of two possibilities. Either the target is less than the middle, or the target is greater than the middle. If the target is less than the middle, then we're going to move high. We're going to move it down to the left so that it now is equal to the element that's just to the left of the middle. Essentially what we're doing is we're going to cut out everything after and including the middle. We're just going to look at the left half of our slice. And that's what moving high down does. Notice that we set high equal to mid minus 1, not mid. We don't need to include mid anymore because we've already proven that it's not what we're looking for. And if that's not true, if target is greater than the midpoint, then we'll do the opposite. Instead of taking high and moving it to the left, we're going to take low, move it to the right. In this case, we're going to move it to equal to be mid plus 1. Again, we're not including mid in the value of low because we don't need to look at mid anymore. So just by moving low and high, you can see that we are going to be shrinking the size of our slice until, again, one of two things happens. Either the middle value is the thing we're looking for, or the size of our slice gets to be 0. If the size of our slice gets to be 0, then that while loop is going to quit, and in that case, just like in linear search, we're going to return a fail condition, or false, depending on how we're doing it. So that's how binary search works. In this slide here, I just want to show you sort of visually an example of what you might expect. So at the top here, we've got an array. You can see all the values in the top row. You can, just for reference points, you can see their indexes on the bottom row. And let's take a look at the left-hand side first. So here we're going to be searching for the value 6. The value 6 is located up here in index 3. We're going to initialize low and high to always be equal to the two ends of our array, so we got 0 and 8. Mid is going to be equal to index 4, so that means our first guess is going to actually be the number 8. Well, 6 is less than the number 8, which means that we have to reassign high to be equal to the value of mid minus 1. So high goes from 8 to 3. Now we're going to calculate a new value for mid. Remember, we're going to be using integer division. That's an important point to remember here. So we're not going to be looking for the box number 1.5. We're going to divide, say 0 plus 3 divided by 2, that's equal to 1. So in this case, we're actually going to go look at index number 1, which is the value 2. So again, it doesn't match. It's actually 6 is greater than 2. So we're getting closer. We're going to reassign the value of low to be equal to mid plus 1. So now low is equal to 2. So again, we've got 2. 2 is less than 3. We're going to go to the middle of 2 and 3, which is index 2, and that means we're going to take a look at the value 5. Again, we don't have a match, but 6 is greater than 5, so we're going to move low to be equal to mid plus 1. Now we've got low equal to 3, high equal to 3. The middle of 3 and 3 is 3, and so it turns out that when we look at the item in index 3, that's the thing we were looking for, so our algorithm can return true. That's an example of a successful binary search. Now let's take a look at the other alternative, which is where you don't find the thing that you're looking for. So we're going to search for 11. If 11 existed in our array, it would have to be, you know, at somewhere between 10 and 25 because we've already sorted the data. So again, we got to start off with 0 and 8. We go to the middle, so we go to look at number 8. 11 is greater than 8, so we're going to take our value for low, and we're going to set it equal to mid plus 1, so the new value for low is 5. The middle point of 5 and 8 is actually 6. That's half of 13. So we're going to go to array index 6. That's 25. That's too high because we're looking for 11. Remember, 11 is less than 25. So in that case, we have to move the value of our high index. High is going to get equal to middle minus 1. So now high is equal to 5. Now low is equal to 5. So the middle of 5 and 5 is 5. We're going to go to the array index number 5, and that's 10. We still don't have a match. So since 11 is greater than 10, we have to move the value of low. And again, as always, low gets the value of mid plus 1. Now low is equal to 6, high is equal to 5. Remember what our while loop condition was. Well, low is less than or equal to high. Well, that's not true anymore. So our while loop just quit. And remember, when our while loop quits, that means we fail. So that in that case, our algorithm would return false. Let's talk a little bit about the efficiency of the two algorithms. And in this case, we're going to think about sort of the worst case. I suppose if you were to consider the best case, linear search is great. If the first thing that you look at in your array is the thing you're looking for, then congratulations. But if you think about it, it really doesn't matter what searching algorithm you use if the first thing you're looking for is the thing, if the first thing that you check is the thing that you're looking for. Although linear search would check array index 0, so that's one example where linear search is actually faster than binary search. But generally speaking, linear search in the worst case is pretty bad, because the worst case would be if the thing that you're looking for is the last item in the array, or if the thing that you're looking for is not in the array at all. And in that case, you would have to look at every single item in the array. In binary search, in the case of binary search, that's not the case, because every time we make a guess, we cut the size of our slice in half. And if you remember back to our discussion of merge sort, the answer to the question, how many times do you have to divide an array in half before you get down to size 1 of your slice, is not n, it's log base 2 of n. And so assuming that your array is sorted, binary search has the potential to run a lot faster. Now you have to pay for sorting. Sorting's not free. So like it says in your book, if you are only going to search a couple times, you might be wasting your time doing binary search. But if you're going to have to do a lot of searching, binary search is definitely going to win in the long run. Okay, so we talked about the basics of searching. We talked about linear search, which is just about the easiest searching algorithm you could ever come up with. And then we talked about binary search, which is a little bit smarter because it uses sorted data and it keeps repeatedly guessing the middle value until it either finds what it's looking for or runs out of things to guess. All right, you're all set.